especially in naval industry. And as you can see, you can just compare these two gears, right? Three gears, right? So here we have human. So now you can have idea about the size of the gear, right? So assume the size of this man as 5.5 feet, right? So I can say this gear pitch circle diameter is around to more than 20 feet, right? And also, similarly, can you see these gears which are located here? So this is a image which is taken using a microscope, and here you can see a small insect. Compared to this insect, uh, you can have idea about the pitch circle diameters of these micro and nano gears, right? So there are gears which are dedicated for such type of very tiny operations, very tiny, very compact gear trains, right? And in moderate level, we have wash gears, which are also compact ones. So, as I told you earlier during bell drive design, so these are not friction drives, these are positive drives, special gears are positive drives, but it follows the uh, principle of friction wheels, right? So the friction wheels are kinematically equivalent to gear drives, where we can consider these as pinion and this right side one as a gear, right? So why two terms? So pinion and gear. So there are two specific terms. We call it pinion and gear. These are the terms, right? So always the pinion is referred to smaller gear, a smaller gear wheel, right? The gear, the term wheel or gear is for the larger one, right? Pinion is for smaller one, and gear or wheel is for larger one, right? And also to avoid any slipping in between gear and the pinion, we have tooth profiles, right? So that is the nature of a gear wheel. Yes, in the case of friction wheels, as you know, the friction F equals mu r is the key factor, governing factor there. So based on the according to the amount of reaction force acting on each wheel, we can calculate the frictional force. That frictional force drives the frictional torque, right? So in gears, the situation is bit different. I will explain you later. But the kinematically, these two are equivalent. So these are the advantages of gear drives. So as you correctly know, it can maintain the constant velocity ratio, not like gears. Can transmit larger power, that is also true compared to belt drives. The efficiency is higher, right? So when it comes to helical gears, it can reach up to 98% of power transmission efficiency. That is quite high. Can be used for small center distance between shafts, and service is reliable with the constant velocity ratios and with high strength. So we can say that the gears are reliable compared to belts. So I'm comparing these gears with belts because you know only about belts at the moment, right? Ability to use in high speed applications, that is also true. Now you can compare with the belts. What happens uh, when we increase the speed in the belt drives? So what happens? You know that due to the inbuilt mass in the belt drives, belt section, there may be some centrifugal forces acting on the belt. So those centrifugal forces will lose the will reduce the grip in between belt and the pulley, and also it will increase the tension in the belt, right? Because due to the centrifugal force acting uh, towards the circumference area, right? So you have a better idea now because we solved few example questions as well. Right, not like that. We can use these gears for very high speed operations and the compact layout and configuration at almost any angle between input and output. So that is also very, very important factor that, as you know, there are some gear trains which are not parallel, or we don't need to worry about the angle in between shafts like gears, sorry, like belt drives. So there are bevels and angled helix gears, right? Bowman wheels. There are plenty of options to combine or transmit power in between angular shafts, right? And there are disadvantages also in gear drives. The manufacturing cost is pretty much higher compared to pulleys and belts, right? So, what is the manufacturing method in the case of gear wheels? Let's say spur gears. So, what is the manufacturing method? Tell me one manufacturing method that can be used for gear manufacturing. Since you are in year two, semester two, you have completed manufacturing process one. Yes, CNC, we can use CNC milling or CNC or EDM wire cut. Yes, casting, good. Lathe machine. Yes, we can manufacture gears using lathe machine, but that is not a feasible option, right? Since there are, yes, the method is also a bit wired, but we can manufacture, but we don't recommend lathe machine for yes. Sometimes based on the material properties we can use, but casting EDM wire cut or CNC milling or conventional milling is the recommended method for gear manufacture, right? Yes, then second point, need of reliable lubricating method for proper operation. Lubrication is a key factor there to reduce the wear in between tooth profiles. Uh, yes, possibility of higher noise in operation due to manufacturing error and the backlash. Right, and also we need to maintain correct center distance as well. In the case of belt drives, you know that the center distance might be slightly varying, right? But depending on the elasticity of the belt, we can manage it anyhow. So, I mean, slight changes are uh, allowed. But in the case of gears, it is essential to maintain correct center distance. Otherwise, there may be higher noise, gear will be locked, or backlash will be increased. Right? So, what do you mean by backlash? Right? So this is the idea of the backlash. You can compare these two figures, right? There is a play in between gears while machine, right? So we call it a gear play, right? So that is the backlash, you know. To avoid the backlash, we need to correctly position the gears, both pinion and wheel. But if there is slight reduction in the center distance, that may be a problem, right? So that is why we put a tiny backlash in time clearance in between gears, So that with the thermal expansion or due to the various environmental changes, gears will not be stuck. Right? So if you can predict the operating conditions, and if you can put a clearance that may be reduced with the operating temperature due to the expansion, that will be better. But to maintain the reliability and the continuous operation, to avoid any disruptions, we basically put a small clearance. We call it a backlash. Right? So and you can see that this is the small increment in center distance. If we can maintain this A center distance, that will be better. But due to uh, unavoidable issues, so due to maintaining correct uh, center distance during the operation, especially during the operations at elevated temperatures, we put this a small gap to maintain a small backlash. So when it comes to accurate or precise operations, so this backlash should be avoided. We need to maintain correct center distance, like in the top image, or else we can use these anti-backlash gears, right? So the backlash is the clearance. So if we can use this the spring tension gear profiles, these gear profiles are concentric, right? So all are tension, as you can see. So it will avoid the backlash. The backlash will be zero, right? See, these are the anti-backlash gears. Right? So these are very much important, but it cannot transmit the huge power, but the error will be zero, right? And also we can allow slight variations in the center distances as well. Then gear classification. Gear classification. Yes, based on the gear tooth profile, we can say that spur gears are there, and these profiles, teeth profiles are parallel. We can say parallel to the gear axis. So this is the gear axis, and the teeth are parallel. And also we have helical gears. Helical gears, teeth are our tooth are oriented in a helix manner, right? So if we wrap a helix around the axis, these profiles are uh, located around along with the helix, right? So what is the advantage of helical gears compared to spur gears, or the advantage of spur gears compared to helix? Is there any plus point or negative points based on your knowledge? Why we use helical gears? I explained during the automobile lecture, right? So these helical gears can transmit higher powers compared to spur gears with similar diameter and similar amount of teeth, right? The power transmission capacity is higher, and in the case of design principles, these spur gears can handle only tangential loads, right? So what do you mean by tangential load? So let me draw. So these tangential loads can be handled. So this load is acting on wheel, and this load is acting on the pinion, let's say. So it can only handle tangential loads, but spur gears can handle both tangential and axial loads. Right? So this is the axial. Right. Then what else? So the operation is quite in helical gears. It generates low noise, because there is a continuous machine, right? So, but in spur gears, we can see some exact pitching point, pitching moment, right? But in helical gears, it's a kind of continuous machine. අපි මේක කොනක ඉඳන් ගානට මෙෂ් වෙලා එන්නේ. ස්පර් ගියර්ස් වල කියනවා සඩන් මැෂින් එකක් තියෙනවා. පිච් පොයින්ට් එකක් තියෙනවා. Right? So that is why the helical gears are mainly used for quiet operations where we need low noise generation. As you know, in the automotive gearboxes, in common gearboxes, helical gears are used to reduce that noise. But in reverse gear, the idle gear is made of spur gear, which generates bit noise. And to avoid backlash and to handle the axial loads, we have double helical wheels, right? So here you can see two gears are there, which are concentric, attached together to handle the axial loads, right? Making an axial load may පැත්තෙන් මෙහෙට axial load axial load cancel, right? And non-parallel gears, you can see that the axis of rotation is here, but so there's a issue in my pointer, right? Anyway, right. So this is the axis of rotation. Our teeth are not parallel, right? So and especially these bevel gears are here to transmit power in between non-parallel accesses, right? So that is very important in the case of power transmission, especially in compact drives, right? So we have intersecting axis. It should not be 90 at all, right? We can change the gear angle, teeth angle to transmit power in between any, right? Any angle, right? I hope you all have seen that type of gears, right? Especially in differentials and especially in geared drilling machines, milling machines. We have such orientation. The motor is placed there. Our power out is there, right? Likewise. And even in the bevels, we have spiral bevels, right? Spiral bevels are also capable of transmitting higher powers, higher torques compared to uh, bevels, right? And also the noise generation is also lower. Yes, so these are the common uh, available drawing of a bevel gear. You can see that there are plenty of details, the angle, teeth angle, the inner diameter, hub diameter, sleeve thickness, like this, right? Um, right, special term, miter gears, right? When the gear ratio is 1, we call it miters, right? And also we have high points and sirens, and spiral and a straight is known, right? Right. In the case of bevel gears, basically we can mount the axles in 90 degrees, and also other angles are possible, as I told you earlier, right? And non-parallel, non-coplanar gears, right? Parallel rukna ek plane එකෙත් නෙමෙයි. Especially spiral gears, and we have worm and wheels, so which can handle very much higher torques and uh, Right. Can you hear me now? Now I'm having issue in my laptop's connection, right? මාරු මාරුවට දෙකේ connecting කියලා වැටෙනවා. Give me 1 minute to solve this one. But I hope now you all can see, right? Right. We were discussing about home and wheel. The main important factor is that this gear setup is having self-locking feature, right? So in the previous cases, can we go back? Yes, in especially in spur gears and helical gears. So let's say this is your driving gear, power input, and this is your output, right? So the power transmission happen this way from input to output and also output to input. Once you rotate the output wheel, the input will be rotated. But in the case of self-locking, so these are non-self-locking gears. But in worm and wheel, so you can transmit the power from worm to wheel, but not in wheel to worm, right? So it will be locked. So that is the self-locking feature in worm and wheel. So that is why these worm and wheel is mainly used in that winder motor. Hope you all you all have seen in automobiles that whenever we cut the power, even though we cut the power, the wheel will not be rotated, even though it is loaded, right? Even though our wheel is loaded, it can handle some amount of torque by limiting worm to rotate, right? So then based on the operating velocity, we can categorize low velocity Yes, again, I am having some issues. Give me 1 minute to change it. Give me Right. Now, so again, right. Uh, then, yes, we were discussing about the external gears and internal gears, track and pinions, and epicyclic gears. So external gears are known, and in the case of internal gears, we can include our gears at the mid area, right? So especially in gear heads, motor gear heads, we have seen this type of gearboxes, right? So shall we arrange one practical to disassemble a gear motor? So what do you think? So I just got the idea, right? I just got the idea, and then you can see the major components in a gearbox, especially. So I think that will be much better, right? What you need to do is assemble and disassemble and assemble the a small gear head, right? We have plenty of geared motors in our workshop, so I will arrange, right? I think that will be much better as a practical. Yes. Um, okay, then rack and pinion. Rack and pinion gears are there. So once you rotate the pinion, the rack will have a kind of reciprocating movement. So these rack and pinions are very much important in conventional older steering systems, right? And epicyclic gear trains, we call it planetary gear trains, sun gear and planet gears are there, especially these type of epicyclic gear trains are included in automatic transmission boxes, right? So as I told you earlier, the smaller profile is called pinion, or the larger profile is called, if it is a cylindrical profile, we call it wheel or gear, right? And as we discussed, we have straight profiles, inclined, helical, and curved profiles, spiral gears, right? So this is quite important, right? As you can see that we can handle six up to six as ratio, velocity ratio, especially using spur gears. Spur gears are not recommended beyond 5 or 6, right? The practical limit is 5, or maximum will be 6, right? So which means the diametral ratio of machine to spur gears will be maximum will be 6, right? So in the case of helical, if our power transmission requirement is higher, the speed ratio is higher, then we can obviously go for helicals. It can reach up to 10, right? The speed ratio will be maximum will be 10. And if we use double helicals, it can reach up to 15. Bevels are recommended up to 4. And here, especially, you can see worm and wheel. The speed ratio can be reached up to 75, right? Type of gears. It is limited to 6 due to the increased wear, right? So if you need to uh, transmit the power in between inclined uh, shafts, then most probably the viable solution will be bevels, right? And pitch line velocity, you can see that self locks, right? It can avoid the axial loads, right? So that is why we have quite higher pitch line velocity capability. In the case of efficiency, as I told you earlier, gears can achieve very high efficiency in the case of power transmission. But the thing is that you can see worm and wheel efficiency is lower. So it can reach up to 98 if the velocity ratio is bit lower, right? So normally in normal scenarios, we say that the worm and wheel efficiency is around 30 to 40. Right. I hope you got some idea about the different gear types, and the efficiencies and applicable velocity ratios. And then gear terminology. So this is very much important in the case of gear manufacturing and design, especially. Yes, we have a lot of terms, right? In the case of gears, what we had is just the groove. measure um, term or the parameter, not the parameter, right? Term, yes, that correct word is term. So this yeah, blue dotted line, right? Hope you all can see, right? This blue dotted line is called pitch circle, right? So this is the arbitrary circle that we consider to measure the diameter of the gear, right? So pitch circle determines the diameter of the gear, right? So this is not a real circle, so it is not tangible, but we consider this pitch circle as the correct diameter of the wheel. So it's a kind of average, but not at all, right? So that is not average. But in normal, in common scenario, we can say that is the average, but it is not, right? I hope you got my idea, right? So if you can measure the distance along with the pitch circle from one point to other corresponding point in the next teeth, it is called circular pitch. If so, that circular pitch should be measured along the pitch circle circumference from where to where? From one point to the next corresponding point. Right? මේ ගිය එකේ මේ point එකේ ඉඳන් ඊළඟ ගිය එකේත් ඒ වගේම point එක වෙනවා. That is called pitch. So similarly, like screws, you know that same idea, right? And let's say yes. Then above the pitch circle line, this face, this surface is called face, right? So face is the area above the pitch circle. Below the pitch circle, we call it flank, face and flank, right? Face and flank, right? Then addendum and dedendum. So when we measure the distance between this pitch circle diameter and the top land, so top land is this face, right? Top surface. So that distance is called addendum, right? So this distance is called addendum. So the distance in between pitch circle and the bottom land. So bottom land is the root here, right? So this is the bottom land is called dedendum, right? So as I told earlier, since we normally in the most of the time we consider pitch circle is the average circle, then addendum and dedendum is equal, right? But not at all, right? So addendum සහ dedendum සමාන වෙනවා. ඒතකොට තමයි ඔය pitch circle එකට අපි average circle එක කියන්නේ. ඒක එහෙම වුණාට එහෙමමයි කියලා එකක් නෑ. Right? So sometimes addendum is lower than dedendum is lower than addendum. එකමද මං කියන්නේ. කොහොම හරි ඔය දෙක වෙනස් වෙන්න පුළුවන්, සමාන වෙන්නත් පුළුවන්. And tooth thickness. Tooth thickness is measured again along the pitch circle diameter to measure the width of, thickness of the tooth, right? From this point to this point. So that is the thickness. If you measure distance from one point to corresponding other point, it will be circular pitch, right? And also this is the addendum circle, and this will be dedendum circle, right? And what else? So that's all. That's all. Yes. Let's see what are the other features remaining during the previous next sessions, right? And then module. Module is the very much important parameter, even though we have different diameters, different number of teeth, the module is the key factor. right? So module is ratio of the pitch circle diameter to the number of teeth. So what do you mean by pitch circle diameter? Diameter of this arbitrary circle, right? So that diameter, right? That diameter is divided by number of teeth. You need to count how many teeth are there, right? One, two, three, four, like us. Let's say our pitch circle diameter is 50 millimeters. And if we have 25 teeth, then module will be 2, right? So there are standard modules, right? There are standard modules. So you can't define the modules. That is the main factor. Right. So these are the recommended series of modules. We have 1, 1.25, 1.52. So why we have defined such a set of modules there? So these values are defined based on the manufacturing methods, right? So in the case of milling machine, so milling manufacturing method, we have profile cutters, right? So this will not be an issue in CNC or not a CNC. CNC EDM wire cut, EDM wire cuts. In the case of EDM wire cut, this will not be an issue, but I mean during spinning manufacturing method, the rotating methods, like CNC milling or conventional milling machines, we have profile cutters, right? So we have profile cutters. Profile cutter will be something like this, right? Again. So I will show you a profile cutter whenever you come to the university. Well, university again, Mama Tama university, right? So I will show you a profile cutter next time, right? So probably we can have a physical lecture as Donald Trump has informed that the war is over. Then probably we can have a physical lecture next time. Then the profile cut is something like this, right? So that profile can be dipped into the shape. These profile cutters are named based on the module size. මේ module size එකට තමයි මේ profile cut එක තියෙන්නේ. මේ පොඩි teeth කපන්න මේ වගේ පොඩි profile cutters තියෙනවා. Right? Right. Then units of the module is in millimeters because number of teeth doesn't have units, right? Then the height of the tooth is about 2.25 times module. So that is a common practice, not a standard value, right? It depends. Okay. Any question up to now? Yes, we have a question. So මේ ගියස් ටිකක් non-parallel, non-coplanar ගියවල ඒකද? ගොඩක් කලින් ආපු message එක මට miss වුණා. So Bhanuka, can you repeat the question? Which gears? අපි 9:11ට මොන හරි දෙන්නේ නැත්තේ. So better if Bhanuka can repeat the question, then I can answer, right? So sorry, I didn't notice that. Yes.
Classification of gears and velocity of gearing part.
Yes. So even though the velocity is classified under different category, so velocity is uniform for all gears, right? So doesn't matter we have a spur or helical or bevel or whatever, spiral or whatever. So based on the velocity we can categorize. The spiral, spur gears, helical are based on the orientation of the teeth. So likewise, we have different categories. Even in the spur gears, we have high, low, and moderate velocities. Even in the helical gears, we have high, low, and moderate speeds. It it is a universal categorization, which means we have helical high speed gears. We have spur low speed gears. So we can intersect. Am I clear? Right, it seems right. Then Right. All the things that we discussed regarding terminology are listed here, right? Yes, one thing, profile, right? Profile was not discussed. So let's discuss about the profile and also the pressure angle. So the pressure angle is the direction of the transmitted forces versus the normal to the central. What does that? Right. So as I told you earlier, is there any possibility to reduce the size? No. Right. Anyway, so suppose we are dealing with involute gears. I will explain you what is meant by involute gears later. But basically, we have two profiles, right? Are in contact. We call it meshing, right? So this is the pitch circle of the lower gear, and this is the pitch circle of the higher gear, right? Sorry, මේක let me erase, right? This one, green color one. Yes, then even though we can see some intersection there, but it is not intersected, right? මේ හරියටම touch වෙනවා මෙතන. So we call it the touch point or pitching point. Yes, then this is the contact point of this profile and this tooth profile, right? So now you need to read this phrase again. Pressure angle is the direction of the transmitted force. What is the direction of the transmitted force? What is the contact point? The contact point is this one, which means once this teeth is going to be contact by rotating in this way, so it will push the green color gear to the downside. So let me so now this is the force acting on the blue color gear. This is the force acting on the blue color one. Force is exerted by green color one. කොළ පාටකින් නිල් පාට මත ඇති කරන බලය. So are you agree with me if I draw a line along with this red color dotted line? Yes, better in on it. So this is the contact point. So I'm pushing this gear profile to the bottom area, this direction. And according to the Newton's third law, there will be a reaction force acting on the red color gear. Red color force is acting on the red color gear by this blue color gear. Nil gear blue name, sorry, red name. That is green color, right? So don't think that I'm color blind, right? මට ඒක වැරදුනා. Right? So that is green color force, right? So now you can understand that this is the direction of the transmitted force. Direction of the transmitted force. It is represented earlier using this red color dotted line. My red color dotted line is in and a direction is in. Pressure angle is the direction of the transmitted force versus the normal to the center line. So what does that mean? What is the center line? What is the center? So this is the center. So in the blue color one, we have center. Let's say the center. In blue color here, we have our center here in blue color here. So I can't draw the center of the uh, green color one. Right? So if we can draw a line in between the green color center and the blue color center, it will be something like this. Right? So this is that center line, maintain a center line, right? This is again pressure angle is the direction of the transmitted force versus the normal to the center line. So this is the normal to the, so this is the center line, right? This is the center line. What is normal to the center line? The center line is normal level. Right, now this is the, so I can't do this with my pointer, right? So that is why I love to have physical lectures, right? Right. So this is the force direction, and this is the normal to the center line. Center line is the normal is the angle between this one, right? So this is the pressure angle. Then may have a pressure angle. Right. So yes, as you can see, these are the pressure angle, common pressure angles. We have 20, 22.2, 25. Right. So that's all. So pressure angle represent the force direction. Pressure angle represent the force direction. Keep that in your mind. Is that clear? Right, then law of gearing, very simple one. Yes, the condition for constant velocity. One thing, common normal. You need to identify a common normal. So earlier we had what? Normal to the center line. So then what does that mean? The common normal, right? So the common normal, the term common normal. So here you can see Mn is the common normal. What does that mean? So now I need to bring you back to the grade 9 or 10 or 7 or 6, I don't know. Right? Whenever you draw a line starting from center to the circumference, all the මොකක්ද ඒකට කියන්නේ චාප දිගට කියන්නේ මොනම චාපයක් තියෙන තැනකට සෙන්ටර් එකෙන් නම් ලයින් එකක් ගහම මෙතන 90ක් වෙනවා. ඔන්න ඔය කතන්දරේ, right? So whenever you draw a radius to a kind of arc, to a type of arc, that the projected angle to the arc will be 90, right? So it is a kind. Now I can say this is a normal to the bottom circle, right? Normal to the bottom circle. Likewise, you can again draw another normal. Let's say from here, this is also a, this is the radius, and this is also a normal. Right? So this is also a normal. This is also a normal. This is also a normal, but it is not common. To become a common normal, right? You need to rotate this into a clockwise, and this need to be rotated counterclockwise. So at one point, we can draw a single line which create a normal to both circles. මේක අරකවල කොහොම හරි මේ හරියට ගත්තට පස්සේ එකම ලයින් එකක් දිගේ මෙන්න මේ ඉරි දෙක වෙන වෙලාවක් තියෙනවා normal දෙකම. එතකොට අපි කියනවා ඒකට common normal එක කියලා. Right? So here our common normal is represented as Mn. You cannot draw any other common normal, right? ඔයාලට එහෙම එකක් පුළුවන් නම් එහෙම එකක් ඇඳලා මට එවන්න. chat box එකේ වෙන common normal එක. So that is the only one, right? The yes, our law of gearing is the common normal at the point of contact between pair of teeth must always pass through the pitch point. What is the pitch point now? Yes, this is the pitch point. As I told you earlier, this is the pitch point. Right? The place where pitch circle diameters are intersecting. Pitch circles, sorry, not diameter, pitch circles are intersect when a point එක තමයි pitch point එක. Right? So this the law of gearing means the common normal at the point of contact between a pair of teeth must always pass through the pitch point, right? It always pass through the pitch point, right? So yes, one thing need to be further explained, right? At the pitch point, common normal at the pitch point. So this is the, sorry, contact point. It also passes through the contact point. So that is the uh, law of gearing, right? Um, then this is the fundamental condition which must be satisfied while designing the profile for the teeth of gear wheels. It is called law of gear. So there are three scenarios, right? It should be a common normal, which should pass through the contact point. Then it will pass through the pitch point, right? So hope you got some idea, right? This is only for your knowledge, right? Then the another law of gearing, the second law, is you need to assume that these gears are as friction wheels, right? So or we can consider the pitch circles in the gears at the pitching point or contact point. The pitch line velocity is similar for both wheels, right? You know how to get the pitch line velocity, V equals R omega equation. The pitch line velocity is similar. If not, which means this cannot be happen in gearing, right? If it is a friction wheel, it is possible, which means it is slipping, right? එකක වේගය අනිත් එකට වඩා වැඩි නම් ඒ කියන්නේ slip වෙනවා. But it is not applicable in gears, right? So why we have two lines there? Because you know that velocities are opposite, right? To get the magnitude, I have put the magnitude mode there, right? And accordingly, we can get the velocity ratio. So the common equation which we use even in the belt drives, belt drive වල පළවෙනි equation එක වගේ එකක් තමයි මේ තියෙන්නේ. The reason why we have this mark is just to consider the velocity, the magnitude only, not the direction, right? Any question up to now? Right. So then gear tooth profiles. This is also quite important. We have majorly two tooth profiles. First one is cycloidal. Then the second one is involute. So this is quite interesting, right? So let me explain the cycloidal shape first. Yes, what do you mean by cycloid first? Cycloid is a curve traced by a point in the circumference of a circle which rolls without slipping on a fixed straight line. To explain you further, I have included one figure at the very at the top, right? At the top, let me show you here. At the top figure, you can see that our circle was initially at center point. So I have selected one trace point which is located on the circumference here. Now I am going to roll this circle. අපි හිතමු මේක ටයර් එකක් කියලා. ටයර් එකේ එක තැනක මම මාක් එකකින් මාක් එකක් දාගෙන මම මේ ටයර් එක රෝල් කරනවා. Next direction එකට. Then I am going to trace the path of this particular mark. මේ point එකේ මම මේක trace කරලා ඒ යන path එක කාට හරි කියනවා වම් පැත්තේ ඉඳන් බලාගෙන ඉන්න කියලා. Right? So that this path will represent the cycloidal shape. So this is not regarding gear profiles, right? Actually, this is regarding gear profile, but this is a mathematical definition, right? Cycloid කියන එක mathematical term එකක්. ඒක define කරන්නේ ඔන්න ඔය විදිහට. Right? So when a circle rolls without slipping on the outside of a fixed circle, අපි මේ line එකක් දිගේ නැතුව, instead of a straight line, if we roll this circle on another roll or on other circle, right? The correct term is circle. මේ roll අපි circle එකක් උඩ roll කරගෙන ගියොත්, the curve traced by a point of the circumference of a circle is known as epicycloid, right? So normally, if it is a straight line, we call it this shape as cycloid, right? So instead of a straight line, if we consider a circle, that the trace line, the trace point or trace line, the created line will be called as epicycloid. Right? අපි මේ උඩ පැත්තෙන් roll කරේ කලින්. දැන් අපි ඒක යට පැත්තෙන් roll කරොත් if we roll the circle on the inside of a fixed circle, it is called as hypocycloid. මේ දෙන යට පැත්තෙන් roll කරපු එක. So then it is called hypocycloid. Right? This cycloid gear profile is created using this both epicycloid shape and the hypocycloid shape. Now you can see that our fixed circle, this fixed circle, so where our, yes, this fixed circle will be treated as, will be served as our fixed circle. Fixed circle, fixed circle, there are two different terms, right? So this is the fixed circle and fixed circle, which will be used to create the epicycloid and hypocycloid. So now you need to pay attention to this pitch circle, right? This pitch circle. At the top, we call it addendum side. We have our epicycloid shape. So from A dash to P dash, A dash to P dash, we have epicycloid shape or profile, while at our dedendum, from P dash to B dash, P dash to B dash, we have our hypocycloid. Is that clear? Is that clear? Right? A cycloidal profile, tooth profile, is a creature of both epicycloid and hypocycloid. But at the top land, it is not just trace point, it is just created by using a parallel offset pitch circle. මේක මේ ආයි trace කරලා නැහැ. මෙන්න මේ shape කෑලි දෙක විතරයි ඔය cycloidal පැත්තෙන් අරන් තියෙන්නේ, right? It is the land එක වෙනම profile. So we are focusing only from A dash to B dash only, right? So all other profiles are based on the just circles, right? So hope you got some idea, right? Any question up to now regarding cycloid gear profiles? Okay. Now again, you can get a better idea. And hypocycloidal land එක අරගෙන ඊට පස්සේ ඉතුරු ටික ගන්න එක තමයි කරන්නේ. මේකෙත් bottom land එක මෙන්න මේ හරියම පටන් ගන්නවා. Main our focus should be given to this profile only. Epicycloidal curve from here to here, pitch circle diameter to addendum, and from here to here, pitch circle diameter to the dedendum. We have this type of feature, right? And also you can notice that we have convex and concave shapes, right? So this is kind of convex and concave shape is also there, right? Yes, you can see how epicycloid profile is contributing to create the, our, what does it mean, our gear profile, right? Now I think it is much clear, right? Now you can see the addendum is here lower than dedendum, right? This is the thing that I told you. It's not always the average. Scale පේනවා. ඇතුල් පැත්තේ roll වෙන එක ලොකුයි මේකේ. පිට පැත්තේ roll වෙන එකට වඩා. What happened? Right. Then the next tooth profile, I think everything is clear regarding cycloidal profile. Then involute profile. So this is not much complex compared to the cycloidal. the thing is quite interesting, right? The involute of a circle is the spiraling curve traced by the end of the imaginary taut string unwinding itself from that stationary circle. මොකක්ද ඒක කියලා ඔයාලා බලන්න. මොකක්ද ඒ කියන්නේ? The involute of a circle is the spiraling curve traced by the end of the imaginary taut string unwinding itself. Right? So basically, in simple terms, in here we have a circle, imaginary taut string. Imaginary on නූලක් කොතල දෙනවා කියලා. So you can get a string or yarn. You need to wind it around the circle, right? Now you need to unwind. Right? So this circle is bearing support, not bearing support. It is fixed, right? So this circle is fixed, right? You need to unwind. Unwind this. So once you are unwinding, that the edge of the string creates this involute shape. මේක දිගාරනකොට අර කොන යන පාත් මේ ස්ට්‍රින්ග් එකේ එජ් එක යන පාත් එක තමයි involute profile එකක් කියලා කියන්නේ. The specialty of this involute is we don't have any concave shapes. We have only convex shapes. මේක එහෙම නැහැ. මේක කලින් තිබ්බ concave shape එකකුත්, right? From here to here concave. Right, so that is regarding involute shape. Here again you can see මේ නූල් කැල දිගාරිද්ද යන පාත්. Right? So the thing, actually, I forgot to mention that regarding the pressure angle, so that the pressure angle is not constant in cycloidal, right? But the specialty in involute shape is that our pressure angle is constant throughout the whole machine, right? As you can see. But in cycloidal, it changing, right? I will explain you later. Right. Right. So these are the advantages of involute gears. The center distance for a pair of involute gears can be varied within limits without change in the velocity ratio. Center distance for a pair of involute gears, involute, can be varied, which means we don't need to maintain the exact center distance for involute gears, right? But this is not true for cycloidal gears. We need to maintain exact center distance to avoid any interferences. So that is the plus point in involve gears. And also the explanation is quite difficult, right? So not the explanation, I mean regarding the designing and the manufacturing is a bit difficult in cycloid, right? Shapes compared to involute. In involute gears, the pressure angle from the start of the engagement of teeth to the end of the engagement remain constant. In involute gears, pressure angle remain constant. Right? Now you can watch this particular GIF again. Right? Now pressure angle, you know how to get the pressure angle. It remains constant. It is necessary for smooth running and less wear of gears. But in cycloidal gears, the pressure angle is maximum at the beginning of the engagement. පටන් ගන්නකොට maximum, then reduce. Right? Reduces zero as the pitch point, start increasing and again becomes maximum at the end of the engagement. Not like this one. Actually, I was unable to find the animation for cycloidal gears, but this angle changes, right? This angle changes in cycloidal gears, not like in involute. The phase flank and of involute gears are generated by single curve. Involute having a single curve, where cycloidal gears double curves are the epicycloid and hypercycloid curves are need to be designed to manufacture face and flank. Thus, involute teeth are easy to manufacture than cycloidal teeth. Actually, not manufacture, let's say, design is quite difficult, right? Then, since the cycloidal teeth have wider flanks, therefore the cycloidal gears are stronger than the involute gears for the same pitch. Yes, flank is quite wider in cycloidal gears. It can handle more tangential loads. Basically, in gears, we consider this teeth section as cantilevered beams. ඔයාලට මතක නේද cantilevered beams? Can you remember in year 1 semester 2 I have explained the cantilevered beams මේ විදියට මේ හරියෙන් cantilever කළා. All right. So then we can apply some loads. So in gear calculations, we assume that these teeth are as cantilevered beams. ඕක දැන් අංශ ගානුවකින් හැරෙව්වට පස්සේ තමයි මේ teeth profile එක එන්නේ. මේවා tangential forces නේ. Whenever the root area or flank area is very dense, so the size of the flank is higher, which means it's something like this one, right? මේ base එක ටිකක් ලොකුයි කියන්නේ. So if the base is or our flank is wider, means it can handle higher loads, right? So that is the point, right? Due to this reason, the cycloidal teeth are preferred, especially for casting. In the case of casting methods, cycloidal teeth, basically cycloidal teeth are preferred to follow casting based manufacturing method. In cycloidal gears, the contact takes place between convex flank and concave surface, where in involute gears, the convex surfaces are in contact. මම කලින් කියපු එක. අරගේ convex concave එකක් තියෙනවා. මේකේ තියෙන convex surfaces. This condition results in less wear in cycloidal gears as compared to involute gears. However, the difference is negligible, right? So, when කොහෙටද දැන් මේ එනවද? So, we have a lot of advantages in involute gears and some advantages is a higher load and manufacturing method is easy in cycloidal. Anyhow, we are focusing towards involute gears, right? In cycloidal gears, the interference does not occur at all, though there are advantages of cycloidal gears, but they are overweighted by greater simplicity and the flexibility of the involute gears, especially that we don't need to much worry about the center distance when we use involute gears, right? So that is why involute gears are much more common in modern machineries, right? The only thing is that the gear interference should be avoided with proper manufacturing methods or proper um, center distance placements, right? So this is the interference happening there. So this basically generate huge noise, huge wear, and also some lowered power transmission. If the gears are locked together, so then it will generate additional resistance to rotate, right? So it will be a kind of loss in terms of power transmission, right? Right. So that is enough regarding interference, right? So we can define based on the maximum addendum and maximum dedendum. Those intersecting points are considered as interference point, right? So MN. So the thing that we need to do is maintain the correct center distance between O1 and O2 to avoid any undercuts, especially the interference in between gears, right? That's all regarding my end for today. Any question remaining? So if you have any question regarding today's session, and please raise them right now. So actually, I'm planning to have one more session on Friday, but I'm not sure. It's not confirmed yet. I'll inform you through your best trip or through an email, possible, right? Right, since you don't have any questions at the moment, and if you have any, please bring them to the next class. Right? And thank you for joining, and have a nice day.